Hi, thank you for this very nice workshop. Can you hear me all right?
Yes, please go on.
Yeah, so we're going to talk about the latency security trade-off. I think this is actually the first concrete, very close latency security trade-off for the longest chain protocols of that type. My co-authors are Jing Li and Ling. Uh, I am from Northwestern University, and this is work in part done together with Jing Li and Ling when Jing was still a PhD student at Northwestern. So what is the fundamental problem we're interested in? And that's the, we like to understand what is the fundamental trade-off between the following properties. One is security, or the probability of a safety violation in the blockchain system. One is the confirmation time, how long we need to wait for a transaction to be confirmed. And the throughput, meaning that the total, in a way, the amount of data that can be confirmed over time, and also the honest to adversarial mining power ratio. In addition to that, the block propagation delay is also a parameter in the system. So throughout this talk, by Nakamoto consensus, I really mean the longest chain protocol in the case of proof of work. So here's the description of the model, and previous speakers have already more or less described it. So here we have a synchrony assumption, and we have this parameter delta, say delta seconds. That's saying all block propagation delays has to be within delta seconds. And because of that, an honest view before time t is then included in all views after time t plus delta. So the protocol is simply to extend the longest blockchain in one's view. So here, in order to do analysis, we will make the assumption, I think it's adopted by many authors, that the honest blocks mined in time, the arrival times, form a continuous time Poisson point process, let's say with rate alpha blocks per second. And then the adversarial blocks are mined also as a Poisson point process, but with rate beta blocks per second. Here we assume alpha and beta are constant, but we are looking at the ratio as a parameter and so on. So we'll see how these parameters will have an impact on the security performance and so on. But they're fixed, no difficulty adjustment. The probability space here in our analysis consists of entirely just mining times. So we're not looking at the blockchains as being part of the probability space. And later I'll point out why this is simple and sufficient. I'm going to define a notion of an achievable security latency function. So by a security latency function, this epsilon, it is achievable if for all s greater than 0 and t greater than 0, there are times. So barring an event with probably no greater than this number, epsilon t of t, all blocks are mined by time s, and also included in some honest miner's longest blockchain at time s plus t, are also included in all honest miners' longest blockchains at all later times. So what I'm saying is a picture like this. So there is a time s and there's time s plus t. So if you find a block that is mined before time s, and you also find it in some longest blockchain after a period of time t, then you believe that it's going to be included in all honest miners' longest blockchains after s plus t. So the in other words, we're saying that it is rare for two longest blockchains after s plus t to disagree about any block mined before s. And this, of course, is the consistency property of this blockchain system. So we have a couple of theorems about this. In fact, we developed both upper bounds and lower bounds, or in other words, the achievability security latency function and also the unachievable security latency function. So I'm going to focus on the achievability part, that what kind of security can I achieve if I'm willing to wait for a certain period of time, and we're going to make it quite close to the lower bound. So here's a first theorem that, in a way, this is no surprise that people have very similar results. But just to help us understand the later one, here we assume the special case where delta is equal to 0. That means that there is 0 block propagation delay. And also in this case, we understand it's a 51% attack. That means that as long as the adversary's mining power is smaller than the honest mining power, so beta is smaller than alpha, then we are fine. So in this case, we have this result that says that for every t, so this is t is basically the confirmation time. The following security latency function is achievable. So if you're willing to wait for time t, then your probability of safety violation is no greater than this. So there's a constant multiplier exponential function in t. So if I graph this, and this is the error probability, and in log and versus the confirmation time is basically a straight line. So we know what the intercept is, and we also know what the slope is in this case. All right, so that's this result, and the way we analyze it is basically we understand in this case when delta is equal to 0, then a private mining attack is the most dangerous attack, and then all we need to do is to analyze a race between an honest miner and collectively all the honest miners and adversarials, and both are Poisson point processes. We can analyze that the probability that one is longer than the other one over after a certain period of time. And so our more significant result is this one. That is for the case that where we have an arbitrary delay. So now delta is arbitrary, so meaning that so this delta is to say that any block mine in the system, once it's published, within time delta seconds, is going to be propagated to all of the miners. So this is an upper bound, okay? The theorem says that we do require that, now we require that the adversarial mining power has to be smaller than alpha times an exponential in alpha times delta. So this is essentially a penalty due to the delay. And we understand that there need to be such a penalty. So the following then security latency function we claim it is achievable. And so here we have two constants, C1 and C2. So essentially it's still an exponential function in time. And we determine the two coefficients C1 and C2 in the paper, and we have analytical forms, and they're easy to calculate. Now the way we analyze it is now we analyzed a different race, and that race is between adversarials and some kind of renewal process I'll describe a little later. And the point here being that, well, the previous author discussed the balancing attack. So in order to establish a result like this, which is an achievability result, we have to care for all kinds of possible attacks. Or in fact, we cannot exhaust all the possible attacks. And thereby we have to prove that regardless of what attack there is, we're going to achieve this, this performance or this level of security. Now, okay, so the exponential function is well understood, that we know that it is exponential in previous work. What is our contribution here is what are these constants? And we make them very close to the actual ones. So these are the, and we're going to show you some numerical plots just to show you we are relatively close in terms of upper bound and lower bound. Here's an example for Bitcoin parameters. Mining rate alpha plus beta is one block in 600 seconds. And the propagation delay here, we'll just take a relatively conservative estimate to say that the upper bound is 10 seconds for a block to be propagated throughout the network. So our the plot is about what is the probability of safety violation versus the amount of confirmation time. And so here, we guarantee the following. We say that if you're willing to wait for about 10 hours, then you're guaranteed 10 to the minus 9, no higher than 10 to the minus safety violation. So if you're willing to wait for, let's say, 4 hours, then they're about 10 to the minus 3. What about the lower bound? So you can also develop, we also develop a lower bound in the paper. It says that, in fact, that you can't do any better, regardless of what you do, you can't do better than this. And this is saying that if you're willing to wait for 10 hours, your security cannot be better than 10 to the minus 12. There is an attack that just violates the safety with probability 10 to the minus 12 if you wait for only 10 hours. So the gap here is about 2 hours or so for a wide range of parameters. Okay, so I forgot to mention that in this case we have the honest mining power is 9 times higher than the adversarial. Now, if this ratio is different, let's say it's a 3-to-1, so honest miner is 75% and the adversarial 25%. Then the achievability is here, the converse is here. So the lower bound is here, upper bound is here, meaning that you have to wait somewhere between, let's say, around 30 hours to accomplish an error probability of 10 to the minus 9. So here in this analysis, throughout we are using confirmation time in seconds or in time, in hours, rather than counting the number of blocks. So for a reason that we can analyze this as well very well. And on the other hand, so the confirmation by depth we find it a little difficult to analyze. Although this can in a way translate to confirmation depth if you want. It's just that that bound is relatively loose in that case, looser than this one, of course. How can we use these kind of results? One of these is to select parameters. To understand that if we change alpha and beta in some way, mining rate in some ways, what's going to happen? So here is a picture of what might happen if we're only interested in 10 to the minus 9 safety violation. So no worse than this. Okay, we want a 10 to the minus 9 at least. And then we look at how much time I have to wait in order to accomplish that. This is hours. How many hours I need to wait? And as a function of the block generation rate. And this, for example, is 400 blocks per hour. Okay, so if my network delay is basically 0, there's blocks are propagated as soon as they're mined, seen by everybody. Then it doesn't matter. You can go as high as you want. So in fact, the higher rate you generate your blocks, the faster you confirm. That's because the faster you see confirmation blocks. Now the picture is beginning to be quite different if there is a delay. So if the delay is 2 seconds, for example, in that case, you can, if you begin to generate blocks faster and faster, at some point the confirmation, it requires longer and longer confirmation time in order to achieve the same security level, to guarantee the same round. I mean, this is an upper bound, so this is achievable. We know this is achievable. Okay, the converse is not too far from this, but I'm only illustrating the achievability part. So if the and this is for good reasons. The reason is that if I have a delay in the system, then I have forking. I have forks. I have the higher the block generation rate, the more forking I have. And so then I have to wait for longer time in order for the change to be confirmed. What about, so if the delay is 6 seconds, then the plot looks like this one. So that means that, well, you probably can generate blocks at about somewhere 150 blocks per hour. If you go to, let's say, 400 or 500 blocks per hour, your confirmation time is going to go up tremendously to many hours. So if then what about 10 seconds? So this is what we used earlier to generate the plot. So if your network delay is 10 seconds maximum, then you can look at that as the block generation rate gets higher and higher. and then we the confirmation time goes down and then it goes up. I think this, by the way, I forgot to mention, in this case I think alpha to beta is I think 3-to-1 if I remember it correctly. So so here is saying we fixed the relative mining rates of the adversarial and the honest miners. It's just that we can adjust the difficulty level to make the block generation faster or slower. So if that's a parameter we can tune, then where would you like it to be? Now this plot is suggesting that Bitcoin is extremely conservative, that we are talking about 6 blocks an hour. And thereby the confirmation time is very high. We mentioned it for 10 to the minus 9, you need to wait for 40 hours, 30, 40 hours to get there. Now, if you make the generation rate a lot higher, let's say around 100 blocks per hour, and in fact, you reduce the confirmation time to a matter of 5 hours. So that's an improvement without sacrificing any security. I say prior to this this theorems and numerical results, we actually don't have a good handle of how to select those parameters. Thereby, the very conservative choices were adopted in all the system designs. So you can then compare all of these different protocols, and they have different block sizes, different block generation rate, and for a given security level, how long you need to wait. And I just want to point out that Ethereum seems to be making fairly good choices at 240 blocks per hour. And because the blocks are smaller, so the maximum propagation delay, you can also think of it as being smaller. The confirmation time is an hour or so for essentially the same. It's very similar throughput as most of the other systems. Bitcoin is definitely on the much more conservative side in terms of all of these. So I'll just mention what goes into the proof to make this work. Because one is that I mentioned that I'm looking at a competition between adversarial mining and also a special type of renewal process. So renewal process essentially is counting the number of so-called loaners. So these are blocks that see no other honest blocks mined within delta time. So there is a loaner. So that's so-called convergence opportunities in another paper a few years ago. So a counting process is a renewal process if the inner arrival times are RID. This loaners, we can't say it's IID, but the first honest block mined after loaner is always a renewal. So we are basically counting that as a surrogate for the number of loaners. So we derive a closed form moment generating function for the inner arrival time and use a turnout type of bounds to develop this probability of safety violation bound, which is the probability no more adversarial blocks are mined than the number of loaners after this duration t. So that's how we develop the bound. I'd just like to mention that how we differ from some of the previous work. So there's trace all the way back to Nakamoto's analysis. But there it is continuous time even, but it doesn't prevent you from some balancing and some other attacks. And those were taken care of first in Garay's paper in 2015. But then there's no delay there and so on. So over time, there have been quite a bit of improvement, but there have been no very close explicit bound up until our work. I think the two notable papers by Ghazi and others and Dembo and others actually found what exactly is the maximum fault tolerance, meaning that what is the worst adversarial mining power we can tolerate. We don't quite get there, but we for Bitcoin parameters, we are very close to that. But when you make the mining rate higher, then there is gap that we need to fill in the future. I'd also like to mention, as I alluded to earlier, our probability space includes only the mining times, not exactly how the blockchains are formed and so on. So we basically claim that regardless of how the blockchains are created, given all these mining times following these statistics, we can bar a small probability event just about the mining time, such that blockchains must have such and such properties. And those are the consistency. And we also prove the liveness in the paper and so This is quite different than the sort of approach adopted by Gary and others, and many others, in fact, that they use a much more complicated probability space determined by the random choices of the random oracle functionality, as well as the private coins of all interactive Turing machine instances. So these models, I say, at least to me, they are very difficult to read. Just to conclude, we developed the first concrete and closed security latency trade-off for the Nakamoto consensus. And these results can be used as to provide guidance on protocol design, including the block generation rates and throughput and so on. And I also argue that a very simple continuous time model is actually often sufficient and easier to work with. Thank you for your attention.